Educational video is brought to you by Vex Robotics Team 438, Metal Gear from Enochs High School. How to hold up an arm and how to problem solve. For the 2011 game gateway, we built a 4-bar lift intended to lift up to 3 game objects. Using 4 motors, the arm could barely lift itself even with full input from the joystick. When you let go of the joystick button, the arm dropped down under its own weight due to the pull of gravity, even though the down button was not activated. We wanted the arm to stay in place if no input was given. Rather than forcing the driver to continually push the up button just to keep the arm stationary, our mentor showed us how to look for solutions on the Vex forum. You'll need to create an account if you don't have one already. Searching for posts with the keywords arm holds position turned up this list of threads. This thread, having a motor hold its position, sounded especially promising. There were quite a few posts, and the most common suggestions seemed to be using elastics and using PID control to program the arm to stay up. Using elastics sounded a lot easier, so we decided to try that first. To attach the elastics, we moved the pivot point on the bar. This freed up a hole for tying and also slightly improved the balance of the arm. The arm still had a tendency to drop, but it didn't drop as much. In addition, the arm gained a full range of motion. However, when the arm was loaded with game objects, the dropping increased. Also, we noticed that over time, the elastics stretched out and were less effective. We decided that in addition to the elastics, we would try a programming solution. PID control was mentioned a lot, but since we were a team of mostly freshmen and hadn't taken calculus, we looked for pre-written code on the forum. The code tab on the forum turned up an example of a basic PID loop in Easy CV4, which we downloaded and pasted into our program. When we ran the program, the arm went berserk. Near the top, the arm raised itself and the driver had to push the arm down to keep it from self-destructing. At other times, the arm refused to move when the driver pushed it up or down, and sometimes the arm just twitched on its own. When we read the documentation more carefully, it mentioned gain values that might need to be tweaked. We tried eliminating the integral and differential components, which stopped the erratic behavior, but the arm was no longer able to lift itself to its full height. Since we had no idea how to tweak the numbers for better performance, we decided to try something simpler. This post recommended finding a mean of the maximum and minimum power needed, and powering the motors at a constant level. We decided to try this with one adjustment. We learned in physics that torque equals RF sine theta, where R is rotation and F is force. So the greatest pull of gravity occurs in the middle of the range, when the angle of the arm is near 90 degrees relative to vertical. To prevent the arm from pushing too high or too low from the constant power, we decided to stop motor power when the angle of the arm, measured by a potentiometer, was above or below a certain level, close to 0 or 180 degrees. It works. The arm consistently reaches its maximum height and does not drop down when the joystick button is released, even when the arm is horizontal, which is maximum torque. It also responds every time the joystick button is pushed. Even though it's simple, the solution works well enough for us. The only drawback of this solution is that near the top of the range, the arm tends to fall a little due to the lack of power above our cutoff angle. The small drop was okay because the arm at rest was still high enough to lift objects to the 30-inch goal, which was good enough to get the job done. Signing off, Vex Robotics Team 438, Metal Gear of Enochs High School.